Hi, I am Dr. Derick Lindquist, and I want to welcome you back to Minding the Mind. I am the Dean of the Jindal School of Psychology and Counseling at the OP Jindal Global University. Today, we're going to talk about synapses, right? This is our second part. In the last episode, we talked about the idea that when an action potential occurs, it leads to the release and clearance of neurotransmitter from the synaptic cleft. Today, we're going to talk about what is the actual effect of that neurotransmitter. Specifically, we're going to ask what happens when the neurotransmitter binds to the postsynaptic receptor. Now again, just so everybody remembers our terminology, we're talking about an axon terminal, our presynaptic terminal, that then forms a synapse with the spine of an opposing neuron. That spine is typically found on the dendrite. Okay? So when the neurotransmitter is released, it is going to bind onto the postsynaptic receptor. Now, those postsynaptic receptors come in two subtypes, two varieties. We have ionotropic receptors and metabotropic receptors. And each of them operate in slightly different ways. But in both cases, again, that neurotransmitter, that ligand, must bind to the receptor in order for it to be activated or open its channel. So let's start with the ionotropic receptor. It's fairly simple. It's actually made of 4 or 5 proteins. They form this ring around a hollow interior. Now, to be clear, as an aside, a receptor, just like any molecule, is actually a very complicated 3-dimensional shape. But for illustrative purposes, it's easy just to think of this as a hollow tube. Okay? So when a neurotransmitter binds to the ionotropic receptor, it basically opens. We now have a hollow interior that allows for ions to flow back or forth. Importantly, ionotropic receptors always remain closed, that is, no ions can flow back and forth, unless and until a neurotransmitter binds. Only at that point do they undergo a conformational change, which allows the ion to flow in or out. Now, we've already talked about the idea of ions flowing in and out of a channel or a receptor, right? Sodium flows in, potassium flows out, chloride flows in. So based on the particular ion and the direction of the flow, we can then either hyperpolarize or depolarize the interior of our postsynaptic terminal. So let's just take 2 examples. Over here on the left, we have what's called a nicotinic receptor. Okay? This is a receptor that binds acetylcholine. So when acetylcholine, the little blue balls there, bind to the receptor, the channel opens, and we have sodium that flows in. Obviously, sodium being a positive ion, it leads to depolarization. So the interior becomes a little less negative or a little more positive. Alternatively, we have a GABA receptor. So when a GABA binds to the receptor and the channel opens, in this case now we have chloride that flows into the interior. Chloride is a negative ion, and so as it flows in, it causes the interior to become more negative. And again, this is what we refer to as hyperpolarization. Now, the second receptor is a little more complicated. It's called a metabotropic receptor, or sometimes called a G protein coupled receptor. The basic idea is that the neurotransmitter binds to the metabotropic receptor, and then we have some proteins that become dissociated, and they come over and they bind to the receptor or channel itself. So we can then open or close these channels as a result of the metabotropic receptor become activated. Now, why this is important is a metabotropic receptor can have multiplicative effects. That is, when the neurotransmitter binds, it can cause not just one channel, but 5 or 10 or 20 channels to then open, allowing ions to flow in or out. So again, it can have a much bigger effect on the voltage of the synaptic terminal than what an ionotropic receptor does. So neurotransmitter binds, it releases the G protein, that G protein binds to a channel, and voila, ions flow in or out. So again, let's look at 2 examples. Now, I just showed you GABA here a moment ago, and if you recall from our last episode, we think of GABA as the primary inhibitory neurotransmitter in the brain because it hyperpolarizes. We already established that with a GABA A receptor, if GABA binds, the channel opens, and we have chloride flow in. Hyperpolarization. Alternatively, GABA B is a metabotropic receptor. GABA binds, it leads to the opening of a channel which allows for the efflux of potassium. Potassium flows out, it takes its positive charge, and the net effect is the same. The inside of that postsynaptic terminal becomes more negative. So, neurotransmitter binds to the postsynaptic receptor, and it generates this charge differential. It generates a change. The interior of that terminal becomes more or less electrically negative. Okay. So we can talk about an excitatory postsynaptic potential versus an inhibitory postsynaptic potential. And keep in mind, here's our dendrite, here's all those individual spines. When an axon and a spine meet, that is our synapse. So for any neuron, there can be tens of thousands, even hundreds of thousands of synapses on a single neuron. And every time an action potential occurs, a neurotransmitter is released, that can lead to an EPSP or an IPSP. EPSP is excitatory postsynaptic potential. It means the interior becomes slightly more positive. It depolarizes due to the influx of sodium. So as the interior becomes more positive or less negative, an action potential is more likely to occur. On the other hand, an IPSP, an inhibitory postsynaptic potential, hyperpolarizes the terminal due to the influx of chloride or the efflux of potassium. In either case, the terminal becomes more negative and the likelihood of an action potential becomes less. Now, to be clear here, when we talked about an action potential, we called it an all or none response because it's always the same in terms of how the shape and the amplitude of the action potential looks. These, on the other hand, are called local or graded potentials. They can be a little, they can be a lot. So with an EPSP, we go more less negative, more positive. So from negative 70 to maybe negative 68 or 65. An IPSP, we go more negative, negative 70 to negative 72, maybe negative 74 or negative 75. So again, the changes can be relatively small. But again, we have to keep in mind the quantity, the overall number of those synapses. 10,000 synapses, 100,000 synapses. So here's the way you can think about it. At each of those synapses, every time an action potential occurs, we have an EPSP that leads to depolarization or an IPSP that leads to hyperpolarization. Some positive, some negative. And this is occurring really almost every waking moment, okay? So you can think of all this information filtering down from the dendrites down into the cell body. Some positive here, some negative there, and it's all percolating downward. We call this an analog signal because it's a spectrum. You have a little bit of positive, a lot of positive, a little bit of negative, a lot of negative. But again, it's all moving downward. And ultimately, what we really care about is the membrane potential of the axon hillock. That's sitting at its resting membrane potential of negative 70. If we have sufficient excitation, that is, enough EPSPs occur close together in time, ultimately that's going to cause the axon hillock to depolarize to threshold. Once threshold is reached, an action potential is automatically generated each and every time. So, in other words, we go from analog signaling, all of these disparate synapses and all these EPSPs and IPSPs, but the ultimate endpoint, the output of the neuron, is a binary signal. An action potential occurs or it does not. There is nothing in between. It's always binary in terms of the output. So this is what we mean by all or none. Once that axon hillock reaches threshold, we have an action potential generated. It travels down into the axon hillock, into the axon terminals. Calcium flows in, Synaptic vesicles fuse and release their contents, and then you activate the postsynaptic receptors of another neuron. Right? This is the process. We iterate it, concatenate it over and over. 1, 2, 3, 10, 100 neurons. But this is the mechanism. This electrochemical signaling, again, is how these neurons are ultimately able to communicate and allow for the processing of information. So how do drugs work? Well, I'm going to go through this a little bit quickly. We can certainly come back and talk about it in a later lecture as we need more detail. But remember, drugs can have two effects. They can be antagonistic or act as an agonist. Antagonistic means you inhibit the action of the neurotransmitter. We can do this by reducing the synthesis, the production, the generation of the neurotransmitter. We can prevent its storage within those vesicles. We can block the neurotransmitter release at the terminal, right? We block those vesicles from fusing and releasing their contents. And we can also block the postsynaptic receptor. So the neurotransmitter is released, but it has no way to bind to the postsynaptic receptor and exert its effects. All of these are antagonistic. All of these are reducing or diminishing the efficacy of the neurotransmitter. On the other hand, we can have agonists. Agonists enhance. Okay? We can increase neurotransmitter synthesis. We can promote the neurotransmitter release from vesicles. We can add more neurotransmitter in each of our vesicles, for instance. We can block reuptake, so it's no longer sucked back up into the terminal. That neurotransmitter remains in the synaptic cleft. Or we can have a drug that actually mimics the neurotransmitter and can bind to that postsynaptic receptor. All of these are agonists, that is, they're going to have a facilitatory effect on the drug. So to finish, let me just give you one single example. Antidepressants, right? Everybody knows Prozac. Prozac is what we call a serotonin selective reuptake inhibitor. Now, we've already talked about reuptake, right? Neurotransmitters release, and then it's retaken back up into the presynaptic terminal. It gets sucked back up in there. So what does serotonin do? Serotonin blocks those transporters, right? You can think of it just kind of a plug, the little blue triangle here. So by blocking reuptake, the effect is that serotonin has nowhere to go. Therefore, its levels will increase in the synaptic cleft. Every time an action potential occurs, you get more serotonin release, but by blocking reuptake, we increase the serotonin levels or the serotonin concentrations within the brain overall. And that, in turn, is thought to have antidepressant effects. So with that, I will conclude. I thank you all. I look forward to seeing you again next time. Bye-bye.